Hello class, welcome to exercise 5b, factorising expressions. This is our second lesson for the quadratics and parabolas unit. Your examples and pre-learning today are going to be example 4, taking out common factors. And the pre-learning for this example will be questions 1, 2 and 3 in the new book and questions 2 and 3 in the old book. Then we'll do example 5, factorising difference of perfect squares. And your pre-learning will be questions 4 and 5 in the new book and questions 4 and 5 in the old book. Then our next example will be factorising difference of perfect squares using surds, where your pre-learning will be question 6 in the new book and question 6 in the old book. And then finally we'll move on to example 7, which is factorising by grouping, where your pre-learning will be question 7 in the new book and question 7 in the old book. The focus of today's class is factorising, and factorising is basically just unexpanding, which is why it was important to start this unit with a lesson on expanding. Factorising quadratics is finding linear binomial factors of quadratic trinomial expressions, i.e. for the quadratic x squared plus 4x plus 3, can we find linear factors x plus a and x plus b, where x plus a times x plus b is equal to that quadratic x squared plus 4x plus 3. Or even for 6x squared plus x minus 12, which is a little bit more complicated because of that 6, is there a times x plus b times cx plus d that end up being the factors of that trinomial. Anyhow, this is the first of 3 lessons where we're going to build up the skills required to find these factors. So strap yourself in, get some cocoa, get your pens, papers, and switch the brains on. Then we'll see you in the introduction where we get things started. Let's start this lesson by learning how to factor by grouping. And we'll sort of take for granted that you have the ability to find a common factor. And so you already know how to use a common factor when trying to factor linear expressions or number expressions. So for example, 30 and 12 have a common factor 6, and 30 and 12 would then equal 6 times 5 plus 2. So no surprises that 42 is equal to 6 times 7. And a linear example would be 5x plus 15. Both have a common factor 5. So 5x plus 15 is actually equal to 5 times x plus 3. And what about the expression x times x plus 2 plus 5 times x plus 2? Well, x plus 2 could just be seen as a common factor. Therefore, we could rewrite that expression as x plus 5 times x plus 2. So let's just take a step back and start with some expanding here as we build up towards factoring trinomials with 2 binomials. All right, so we know that x plus a times x plus b is equal to x times x plus b plus a times x plus b. And then expanding that one more time, we get x squared plus bx plus ax plus ab. So this means that the reverse is also true. So if we start with the expanded version of that product of binomials, and if we look at this part on the left and this part on the right, this is what we mean by grouping. And to take out the common factors of each group, we have x for the group on the left and a for the group on the right. And now because x plus b is a common factor, we can rewrite that as x plus a times x plus b. Now this method of grouping will work with any trinomial, x squared plus bx plus c, providing that the factors of c add up to b. And we'll go into that in much more detail in our next lesson. There are also other tricks that we can use to make it quicker to factorise trinomials, such as finding shortcuts with perfect squares or difference of perfect squares. So recall from our last lesson that if we have a perfect square, x plus a squared, well that's just equal to x squared plus 2ax plus a squared. And that difference of perfect squares was all about x plus b times x minus b is equal to the square of x minus the square of b. Well, because we showed these facts in our last lesson, it's also true that the reverse is true. So for example, if you had x squared plus 2ax plus a squared, well that can just be factored as x plus a squared. And if you saw an expression x squared minus b squared, well that could be factored as x plus b times x minus b. So in today's lesson, we'll be looking for difference of perfect squares, or the ability to group a trinomial together and find that common factor. All right, so that's the end of the introduction. I'll see you in the next section. So we covered expanding in our last lesson, so you should be able to recall that a times b plus c is equal to a plus b times a plus c. And as we said in the introduction, factoring is just doing the reverse. So if you were presented with the expression AB plus AC, well, A is a factor for AB and AC. So you'd then just factor that by saying A times B plus C. And you should also recall that x plus A is just a number. So I could factor in the same way by saying 3 times x plus A plus 2 times x plus A is just 5 times x plus A. And adding in some algebra, x times x plus A plus b times x plus A is x plus b times x plus A. And it was important to bring that up because some people might see all the x's and the b's and the a's and get lost. But it's pretty obvious that if you got 3 of something and 2 of something, you got 5 of it, right? Anyhow, let's just move on to example 4, where we're going to factorize the following expressions. In part A, we have minus 3x minus 12. And these both could be rewritten as minus 3 times x and minus 3 times 4. So clearly minus 3 is the common factor. So taking that out the front, we have minus 3 times x plus 4. And in a question like this, you really do need to be careful with those negatives. All right, let's move on to part B, where the expression is 20 times a squared plus 30a. Now, because 20a squared is equal to 2 times 10 times a, and 30a is equal to 3 times 10 times a, I can see that 10 and a are factors of both of those. So therefore, I'm going to factorize this expression as 10a times 2a plus 3. And that's because after I've taken the 10a out of 20a squared, I've got 2a left. And after I've taken the 10a out of 30a, I've got 3 left. All right, let's move on to part C, where the expression is 2 times x plus 1 minus a times x plus 1. So let's not forget that x plus 1 is just a number or term. And I'm multiplying it by 2 and by negative a, so therefore our answer is 2 minus a times x plus 1. Okay, before we finish this section, I thought I'd just give you a pro tip. And that is, if you finish a question and you're not 125% confident of your factorising, well, just expand your answer and see if it returns you to the question. So let's do that with each one of these examples. So for question A, we ended up with minus 3 times x plus 4. Well, that's equal to minus 3 times x plus minus 3 times 4, which equals minus 3x minus 12, which is exactly what the question was. All right, part B, we ended up with 10a times 2a plus 3. So expanding, that means we get 10a times 2a plus 10a times 3, which is equal to 20a squared plus 30a, which is what the question was. And for part C, our answer was 2 minus a times x plus 1. And using FOIL, we end up with 2x plus 2 minus ax minus a. And the question for part A was 2 times x plus 1 minus a times x plus 1. Well, if we expand each of those brackets, we end up with 2x plus 2 minus ax minus a. And hey presto, we've got the right answer. All right, with that, I think you should pause the video now and do questions 1, 2, and 3 in the new book, or questions 2 and 3 in the old book. And then I'll see you in the next section. We already know that a squared minus b squared will equal a plus b times a minus b because of the difference of perfect squares. However, sometimes you might come across 2a squared minus 2b squared. It isn't obvious that it's a difference of perfect squares, but if you remove that common factor, we end up with 2 times a squared minus b squared. So we've now got that difference of perfect squares. So this will be equal to 2 times a plus b times a minus b. And in this section, that will be your only real complication. All right, let's move on to example 5. where we're going to factorise with the difference of perfect squares, but always watching out for those common factors. Alright, part A, we have x squared minus 16. So clearly there's no common factors here. That's just equal to x squared minus 4 squared, which is equal to x plus 4 times x minus 4, because clearly they're difference of perfect squares. Alright, let's move quickly on to part B, where we have 9a squared minus 4b squared. Once again, clearly no common factors. So I'm not sure if this is necessary for everyone, but while we're learning, I do like to really make it explicit where the squares are. So 9 squared is 3a squared. Okay, you know you square everything inside those brackets. And 4 squared is 2b squared. So this really does make it obvious what is being squared to make those terms. Alright, so using difference of perfect squares, we now have 3a plus 2b multiplied by 3a minus 2b. As I said, by difference of perfect squares. Alright, let's move on to part C, where we have 12 times y squared minus 1200. Alright, so it's not apparent here that they're squares, but that's because 12 is a common factor. And clearly y squared is a square and 100 is equal to 10 squared. So leaving the common factor out the front, y squared minus 10 squared is y plus 10 times y minus 10, using the difference of perfect squares. And in part D, we have x plus 3 squared minus 4. Now 4 is just equal to 2 squared. That makes this x plus 3 squared minus 2 squared. So let's not forget that x plus 3 is just a number, right? So we actually do have difference of perfect squares here, because we got x plus 3 plus 2 times x plus 3 minus 2. And of course that's because x plus 3 is just a number squared. And once you've done this, you want to clean up those brackets, so we're left with x plus 5 times x plus 1. Okay, if you're not sure, 3 plus 2 is equal to 5, and 3 minus 2 is equal to 1. So just as a pro tip, x plus 3 is still a perfect square, so don't be confused. Anyhow, if you are, we'll definitely go over that again in the classroom. But right now, you should pause that video and do questions 4 and 5 in the new book, and questions 4 and 5 in the old book. And then hurry back and we'll see you in the next section. Finding the difference of perfect squares can almost seem too good to be true. I mean, how often will both terms be squares? So what about x squared minus 5? Will difference of perfect squares still work? Well, the answer is yes. And that's because the square root of 5 squared is equal to 5. So we could rewrite x squared minus 5 as x squared minus the square root of 5 squared. And then using the difference of perfect squares, that's equal to x plus root 5 times x minus root 5. Alright, let's put this into action with example 6, where we're going to factorise with difference of perfect squares and surds. Okay, first up in part A, we've got x squared minus 10. So we know that's equal to x squared minus the square root of 10 squared. So therefore we have x plus the square root of 10 times x minus the square root of 10. Alright, let's move on to part B, where we've got x squared minus 24. And you know that's equal to x squared minus the square root of 24 squared, which is equal to x plus the square root of 24 times x minus the square root of 24. However, we don't stop here, because the square root of 24 is equal to the square root of 4 times 6, which equals 2 times the square root of 6. Okay, so let's rewrite that out as x plus 2 times root 6 times x minus 2 times root 6. Alright, that's much nicer. And finally, in part C, we have x minus 1 squared minus 5, which is equal to x minus 1 squared minus the square root of 5 squared. And by this stage, you should be really comfortable seeing x minus 1 as a number. Therefore, that leaves us with x minus 1 plus the square root of 5 times x minus 1 minus the square root of 5, with these x minus 1s representing the insides of this perfect square. And another pro tip for today is you must be really careful of that plus and minus sign in part C. In other words, the x minus 1 stays the same, but we have a plus root 5 in one and a minus root 5 in the other. All right, so just keep an eye out for that. But right now you should pause that video and do question 6 in the new book and question 6 in the old book. And then I'll see you in the next section. This 2-step process is fundamental for the following 2 lessons. I can't really understate how important it is. All right, let's recall from the introduction that x times x plus b plus a times x plus b is equal to x plus a times x plus b. In this lesson, sometimes you're going to find that we need to find that x plus b. So let's see an example like that with example 7, where the expression we start with is x squared minus x plus ax minus a. So the first thing we do is group these, and then we can find a common factor in each group. So the one on the left has x, so that leaves us with x times x minus 1. And the one on the right has a common factor of a, so we've got a times x minus 1. And that's just by finding common factors in each group. And doing so, we've found our x plus b, so to speak. So we've now got x plus a times x minus 1. And we factored it, so well done to us. Just one other pro tip. What if you get an expression x squared plus ax minus x minus a? So a group on the left has a common factor of x, but the group on the right doesn't seem to have a common factor. But the trick here is that the common factor is minus 1. So therefore we end up with x times x plus a minus 1 times x plus a. You don't always have to write that 1 as well, and sometimes this common factor might be positive 1. Anyhow, we can now factor that as x minus 1 times x plus a. But more about this in our next lesson. In fact, I'm going to give you an example with numbers as a heads up to our following lesson. And when I say numbers, I mean some coefficients for our terms. So let's write out x squared plus 2x minus 3x minus 6. Okay, so we've got one group on the left and one group on the right. Common factors for the one on the left is x, and common factors for the one on the right is minus 3. And we now have x minus 3 times x plus 2. Alright, so I haven't started off with a well-known trinomial there. It's written out in an easy way to find some grouping. We're going to learn that in the next lesson. But I do want to point out to you why it's really important that you have a good grasp of this grouping skill or finding common factors like this. Alright, so let's just pause that video now and work on question 7 in the new book or question 7 in the old book. And then come back and we'll summarize this lesson. And it is really important to summarize this lesson. Alright, as I've stated many times, we'll be using grouping over the next 2 lessons. So this makes it really important that you understand that x times x plus b plus a times x plus b is equal to x plus a times x plus b. And we've used difference of perfect squares many times in this lesson, but it's really important that you note that difference of perfect squares require a negative sign. So what I mean by that is if we took x squared plus 4, well, that's equal to x squared minus 4. And then using what we know, that ends up being x squared plus the square root of negative 4 times x squared minus the square root of negative 4. And hopefully you know by now that the square root of a negative number is not a real number. So it is really important that there is that negative sign there. Alright, in this lesson, a successful student will understand what it means to write an expression in factorised form, know to always look for common factors before trying any other factorising techniques, be able to recognise a difference of perfect squares, including ones that involve surds, be able to factorise using a common factor or difference of perfect squares, and finally be able to use the grouping technique to factorise. Okay, good luck with all that. I hope you master it all. Keep working hard and we'll see you in the next lesson, be that the video or in class. Bye.